Welcome everyone to Azure Route Server. Today we're diving deep into Azure Route Server, one of Azure's most powerful networking services for hybrid cloud connectivity. In this presentation, I'll walk you through what Route Server is, why you need it, and most importantly, how to implement it step by step. This isn't just theory. We'll cover real commands and practical scenarios you'll encounter in production. Think of Route Server as the traffic director for your Azure network. It enables dynamic routing between your network virtual appliances and Azure's software-defined network, making hybrid connectivity much more intelligent and automated. Understanding Route Server architecture. Let me show you how Route Server fits into your network architecture. This diagram illustrates the core components and their relationships. Notice how Route Server sits in its own dedicated subnet. This is mandatory and must be named exactly Route Server Subnet. It acts as a BGP route reflector, establishing peering sessions with your network virtual appliances. The beauty of this design is that Route Server automatically programs Azure's SDN routing tables based on the routes it learns from your NVAs. This means traffic can flow intelligently between Azure subnets and on-premises networks without static routing. What's particularly elegant is the active deployment across availability zones, giving you built-in high availability without additional configuration. East-west traffic flow. Now, let's examine how traffic flows between different subnets within your Azure virtual network. This is what we call east-west traffic. In a traditional setup, VMs in different subnets communicate directly. But with Route Server and NVAs, we can insert security policies and inspection into this traffic flow. Watch this sequence. When VM1 needs to reach VM2 in a different subnet, it first consults the routing table. Route Server has already programmed this table with routes learned from the NVA via BGP. The traffic then flows through the NVA, where you can apply firewalling, intrusion detection, or any other network security functions before reaching the destination. This gives you centralized control over inter-subnet communication. North-south traffic, which is traffic between your Azure environment and on-premises networks, is where Route Server really shines. Here's the magic. Your NVA learns routes from on-premises via VPN or ExpressRoute, then advertises these routes to Route Server using BGP. Route Server then automatically programs these routes into Azure's routing infrastructure. This means when an Azure VM needs to reach an on-premises server, the traffic automatically flows through your NVA, where you can apply consistent security policies across your hybrid environment. The return path works the same way. Route Server advertises Azure subnet routes to your NVA, which can then propagate them to on-premises routing tables. Let me break down the BGP route learning and advertisement process, because understanding this is crucial for troubleshooting and optimization. It starts with your NVA learning routes from on-premises through whatever connectivity method you're using, such as VPN, ExpressRoute, or even internet-based connections. The NVA then establishes BGP peering sessions with Route Server and advertises these learned routes. Route Server receives these advertisements and programs them into Azure's software-defined network. What happens next is automatic route propagation to all VMs in your virtual network. This entire process is dynamic, so when routes change on premises, they're automatically reflected in Azure within minutes. Before deploying Route Server, let's cover the prerequisites and key requirements you need to understand. First, the Route Server subnet requirement is non-negotiable. It must be named exactly Route Server Subnet and be at least a /27 in size. You cannot place any other resources in this subnet. You will also need a standard SKU public IP address. Remember that Route Server uses BGP AS number 65515 by default. This cannot be changed. For your NVAs, ensure they support BGP and can establish peering sessions. Plan your AS numbers carefully. Use private AS numbers in the 64512 to 65534 range for your NVAs. Also, consider that Route Server has a limit of 1,000 routes per BGP peering session. If you have large routing tables, you might need route summarization. Step 1. Creating the Route Server subnet. Let's start with the foundation, creating the dedicated subnet for root server. This is always your first step, and getting it right is critical. Notice the subnet name must be exactly root server subnet. Azure is case sensitive here. The 27 prefix provides 32 IP addresses, which is the minimum required. I typically recommend using a 26 or larger if you have the address space, just in case you need to expand or if Azure introduces new features requiring additional IPs. This subnet will be entirely dedicated to root server instances. You cannot deploy any other resources here, not even a simple storage account or network interface. Step 2. Creating the public IP next. We need a public IP address for root server. This isn't optional. Root server requires a public IP even though your BGP peering will happen over private IP addresses. Pay attention to the SKU requirement. It must be standard SKU. Basic SKU public IPs won't work with root server. Also notice we're using static allocation, which is required. This public IP is used for root server management and some external BGP scenarios. Even if all your BGP peering is internal, root server still needs this public IP for its control plane operations. The creation is straightforward, but make sure you're in the same resource group and region as your virtual network. Step 2. Creating the public IP next. We need a public IP address for root server. This isn't optional. Root server requires a public IP even though your BGP peering will happen over private IP addresses. Pay attention to the SKU. Step 3. Deploying root server. Now we're ready to create the actual root server instance. This is where everything comes together. The subnet, the public IP, and the root server service itself. Notice how we reference the root server subnet using its full resource ID. This ensures we're targeting the exact subnet and avoids any ambiguity. The deployment typically takes 15 to 20 minutes, so this is a good time for a coffee break. Azure is deploying root server instances across multiple availability zones for high availability. During this time, Azure is also setting up the BGP infrastructure, allocating the internal IP addresses that your NVAs will peer with, and preparing the routing control plane. Step 4. Configuring root server settings. After root server is deployed, we need to configure some important behavioral settings that control how it handles different types of traffic. The Allow B2B traffic parameter enables branch-to-branch communication. When set to true, traffic from one on-premises site can reach another on-premises site via Azure, using root server to facilitate the routing. The Allow transit parameter is equally important. It allows transit routing through your NVAs. Without this, root server won't propagate routes that would cause traffic to transit through your virtual network. Both parameters default to false, so you need to explicitly enable them if you want these capabilities. In most enterprise scenarios, you'll want both enabled. Step 5. Creating BGP peering. Now comes the heart of root server functionality. Establishing BGP peering with your network virtual appliances. Each BGP peering session connects root server to one NVA. You specify the NVA's private IP address and its BGP AS number. Remember, each NVA should have a unique AS number. The peer IP address must be reachable from root server. This means it should be in the same virtual network, or a peered virtual network. The NVA must also be configured to accept BGP connections from root server's IP addresses. For high availability, I recommend creating multiple BGP peering sessions with different NVAs. Root server will load balance traffic across multiple paths automatically. Step 6. High availability setup. Speaking of high availability, let me show you how to set up a second BGP peering session for redundancy. Notice how we're using a different AS number for the second NVA. This is important for proper BGP behavior and loop prevention. With multiple BGP peering sessions, root server will receive the same routes from multiple NVAs. It uses standard BGP best path selection to choose the optimal route, but it also programs backup routes automatically. This means if one NVA fails, traffic will automatically fail over to the backup NVA within seconds. The failover is handled entirely by Azure's routing infrastructure. No manual intervention required. Step 7. Verification commands. After configuration, verification is crucial. These commands help you confirm that root server is working correctly and troubleshoot any issues. The first command shows the overall status of your root server instance. Look for provisioning state, succeeded, and note the virtual router IP addresses. These are what your NVAs will peer with. The BGP peering list command shows the status of your peering sessions. Connection state. Connected means BGP is established successfully. If you see connecting or failed, there's likely a configuration issue either on root server or your NVA. The most common issues are incorrect IP addresses, AS numbers, or firewall rules blocking BGP traffic on port 179. Step 8. Root learning verification. Now let's verify that routes are being learned correctly. This is where you can see root server in action, learning routes from your NVAs. The learned routes command shows what routes root server has received from a specific NVA. You should see your on-premises network prefixes here, along with any other routes your NVA is advertising. If this list is empty, check your NVA configuration. Make sure it is advertising routes in its BGP configuration. Also verify that the routes exist in the NVA's routing table to begin with. Each route entry shows the network prefix, next hop IP address, and AS path. The AS path shows you the BGP autonomous systems the route has traversed. Step 9. Route advertisement verification. Just as important as learning routes is advertising them. This command shows what routes root server is advertising to your NVAs. You should see all your Azure Virtual Network subnets listed here, plus any routes from peered virtual networks if you have virtual network peering configured. This is how your NVAs learn about Azure networks and can route traffic back to Azure from on-premises. If your NVA isn't receiving these routes, check its BGP configuration and make sure it's accepting route advertisements. The advertised routes also include any routes that root server has learned from other NVAs, enabling branch-to-branch communication through Azure. Let's look at the component dependencies overview. I'll show you a visual representation of how all the root server components depend on each other. Understanding these dependencies is crucial for deployment planning and troubleshooting. Everything starts with your virtual network and the root server subnet. Without these foundational components, nothing else can be created. The public IP can be created independently, but it must exist before you can create the root server instance. Once root server is deployed, you can start creating BGP peering sessions. Each BGP peering session requires corresponding NVA configuration. This is often where things go wrong. Make sure your NVA team coordinates with your Azure team to ensure both sides are configured correctly. The final step is route learning and advertisement, which happens automatically once BGP sessions are established. Complete deployment workflow. Here's the complete workflow from planning to production. I recommend following this sequence to avoid common pitfalls and ensure a smooth deployment. The pre-deployment phase is often underestimated, but proper planning saves hours of troubleshooting later. Make sure you have your IP address spaces planned out and your NVA requirements clearly defined. During deployment, stick to the sequence we've covered. Don't try to create BGP peering before root server is fully deployed. It will fail. The configuration phase involves coordination between teams. Make sure your network team configures the NVAs properly for BGP peering. Finally, validation is critical. Don't assume everything is working just because the commands succeed. Test actual traffic flow and verify that routes are being learned and advertised correctly. Monitoring and troubleshooting. Once root server is deployed, ongoing monitoring becomes important. These commands help you maintain visibility into your routing infrastructure. The monitoring commands should be part of your regular operational procedures. I recommend checking BGP session status daily and route learning status weekly. For troubleshooting, start with the basics. Verify BGP session connectivity, then check route learning and advertisement. Most issues stem from configuration mismatches between root server and NVA settings. Common issues include incorrect AS numbers, IP address mismatches, firewall rules blocking BGP traffic, and NVAs not advertising routes properly. Remember that BGP is a complex protocol. Small configuration errors can have big impacts. Always verify changes in a lab environment before applying to production. Best practices and limitations. Let me share some important best practices I've learned from implementing root server in production environments. High availability is non-negotiable. Always deploy multiple NVAs with BGP peering. Use private AS numbers for your NVAs to avoid conflicts with public internet routing. IP planning is crucial. Reserve sufficient address space for future expansion. The root server subnet cannot be resized easily once created. Be aware of the limitations. Root server uses a SN 65515 and you cannot change this. The 1000 root limit per BGP session can be a constraint in large environments. Not all Azure regions support root server yet, so check availability before making architectural decisions. Also, ensure your team has BGP expertise. This is not a set and forget solution. Conclusion and next steps. We've covered a lot of ground today, from root server architecture to hands-on implementation with real Azure CLI commands. The key takeaways are: root server enables dynamic routing in hybrid environments. It requires careful planning and coordination between teams, and proper verification is essential for successful deployments. Your next steps should be to lab this in a development environment. Practice the commands we've covered, and start planning how root server fits into your organization's network architecture. Remember, root server is a powerful tool that can greatly simplify hybrid network routing, but it requires proper understanding and configuration to work effectively. Thank you for your attention, and I'm happy to take any questions about Azure Route Server implementation.